Hello everyone, in this video we shall be discussing the concept of valency. This video has been split into two sections in order to facilitate assimilation and aid better understanding. You can find the second part in my channel, and by the way, do not forget to like, comment, share and subscribe. Without further ado, let's begin. Valency is also known as valence, and it is simply defined as the combining power of an element. This can be further explained as the combining capacity of one atom of such element with atoms of other elements to form a chemical compound. To consolidate our understanding, let's take a look at a few examples. Considering the cations sodium, magnesium, and aluminium, and the halogens as our anions, chlorine, bromine, and iodine. Sodium has a valency of 1, indicated by the single positive charge on the atom of sodium, while magnesium has a valency of 2 and aluminium has a valency of 3. The halogens have a valency of 1, indicated by the single negative charge on the halide ions. Permutating between the aforementioned ions, if sodium and chlorine were to combine, we would need just one chlorine atom to combine with one sodium atom to form sodium chloride. This is because the valency of sodium is 1, while the valency of chlorine is as well 1. So in the sodium chloride compound, we find just one atom of chlorine and one atom of sodium. Our second example, let's consider magnesium. If magnesium were to combine with chlorine to give magnesium chloride, because the valency of magnesium is 2 and the valency of chlorine is 1, it implies that we would need 2 chloride ions to combine with 1 magnesium ion to give magnesium chloride. 2 chloride ions is needed because the valency of magnesium is 2, while 1 magnesium ion is needed because the valency of chlorine is 1. Third example, if aluminium were to combine with, say, bromide ion, it implies that we would need 3 bromide ions to combine with 1 aluminium ion to form aluminium bromide. The reason for this is because the valency of aluminium is 3, while the valency of bromine is 1. So it implies that we need 3 bromide ions in order to combine with aluminium, because the valency of aluminium is 3, while we need just 1 aluminium ion to combine with bromine, because the valency of bromine is 1. I hope that is clear. Before we proceed, let's look at one more example. Say between aluminium and oxygen. As we've seen earlier, aluminium has a valency of 3 and oxygen has a valency of 2. If aluminium and oxygen were to combine to form a compound, we would need 3 atoms of oxygen to combine with 2 atoms of aluminium, so therefore we'll have aluminium oxide. It is indicated within the compound of aluminium oxide that we have 3 oxygen atoms and 2 aluminium atoms. So these examples that we've seen so far has shown us the capacity by which these atoms combine with each other to form chemical compounds. So that is invariably what is meant by valency. Valency can also be defined in terms of hydrogen. So in this case, valency is the number of hydrogen atoms that will combine with one atom of such element to form a compound. That is the number of hydrogen atoms that is required to replace that atom in a chemical compound. So to quickly understand this definition, let's use the same examples, the same ions that we mentioned earlier. That is sodium, magnesium, aluminium, and oxygen. So if sodium and hydrogen combines, because the valency of sodium is 1, we will need just 1 hydrogen atom to combine with sodium to form sodium hydride. Now, if it were magnesium, because the valency of magnesium is 2, we will need 2 hydrogen atoms to combine with magnesium to form magnesium hydride. If it were aluminium, because the valency of aluminium is 3, we would need 3 hydrogen atoms to combine with aluminium to form aluminium hydride. Now, if oxygen combines with hydrogen, because the valency of oxygen is 2, we will need how many hydrogen atoms? Yes, you guessed right, 2 hydrogen atoms to form the compound dihydrogen oxide. that is popularly known as water. When it is said that the valency of an atom or radical is so and so, it can imply two things. Firstly, it could imply the number of positive or negative charges carried by ions of such elements or radicals. Or it could imply the number of electrons lost, gained, or shared by atoms of that element during chemical combination. So let's look at some examples for the first case. In this case, we already mentioned some ions prior. Sodium ion, calcium ion, magnesium ion, aluminium ion, chlorine ion, bromide ion, oxygen ion, nitrogen ion, and some radicals or polyatomic ions such as hydroxyl ion, bicarbonate ion, hepta-oxodichromate 6 ion, ammonium ion, phosphate ion, etc. So going by this definition, we would find out that the number of charges on sodium in this case is just a single positive charge. So it means that the valency of sodium is equal to 1. The number of charges on calcium is 2 positive charges, so the valency will be equal to 2. So is magnesium, the valency will be equal to 2. Now the number of charges on aluminium is 3 positive charges, so valency equals to 3. Going by that, the number of charges on chlorine and bromine is a single negative charge on each of them, so their valencies equals to 1 each. Number of charges on oxygen is -2, so valency of oxygen will be equals to 2. Then valency of nitrogen in this case will be equal to 3. Now going to the radicals, the number of charges belonging to hydroxyl ion altogether is -1. So the valency of hydroxyl ion in this case will be 1. We ignore the charges when we're talking about valency. Take note of that. The total number of charges on bicarbonate ion in this case is a single negative charge. So therefore, the valency of bicarbonate ion is equal to 1. The total number of charges on phosphate ion is 3. 3 negative charges. Therefore, the valency of phosphate ion is 3. The valency of ammonium ion, as indicated here because of the single positive charge, is 1, while the valency of hepta-oxodichromate 6 ion is 2. I hope that is clear. Going by the second definition, valency could also imply number of electrons lost, gained, or shared by atoms during chemical combination. Take for example sodium. If sodium were to ionize, it does so by an electron loss, as written in this equation. Because sodium ionizes by losing just a single electron, then we say the valency of sodium is 1. If calcium ionizes, it does so by electron loss. So calcium ionizes by losing 2 electrons. So because calcium loses 2 electrons during ionization, then we say the valency of calcium is 2. When chlorine ionizes, it does so by electron gain to form chloride ion. So because chlorine ionizes by losing a single electron, then we say the valency of chlorine is 1. If oxygen ionizes, it does so by gaining 2 electrons to form oxide ion. So because oxygen ionizes by gaining 2 electrons, then we say the valency of oxygen is 2. In the case of carbon, that usually forms covalent bonds with other elements. Take for example in methane. Carbon goes into covalent bond formation with 4 hydrogen atoms to form methane. Because in the formation of methane, carbon shares 4 electrons with 4 hydrogen atoms, then we say the valency of carbon in methane is 4 because carbon donates 4 electrons to participate in covalent bond to form methane. Have you ever wondered why elements possess the specific values of valencies that they do? For example, why does sodium possess a valency of 1 and not 2 or 3? Also, why does oxygen possess a valency of 2 and not 3 or 1? The major reason for this is because of what is called the octet rule. The octet rule states that in the formation of a chemical compound, atoms lose, gain, or share electrons in order to achieve the stable octet configuration like noble gases. Before we explain further what we just said, let's take a look at the first 30 elements of the periodic table. The first element of the periodic table is hydrogen, then followed by helium. Then we have lithium, followed by beryllium, then boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, potassium, calcium, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. These are the first 30 elements. The noble gases belong to the group 8A of the periodic table, and they include helium, neon, argon, krypton, xenon, and radon. They are called noble gases because of the virtually unreactive nature of these elements towards other elements in the periodic table. This is because of the special stability associated with the octet electronic configuration of their outermost shell. Take, for example, neon with atomic number 10 and argon with atomic number 18. Neon has the electronic configuration 2, 8, 2 electrons in the K shell and 8 electrons in the L shell. Now the same thing applies to argon with atomic number 18. It has the electronic configuration 2, 8, 8, 2 electrons in the K shell, 8 electrons in the L shell, and 8 electrons in the M shell. The outermost shell for neon is the L shell, and it has 8 electrons, while the outermost shell for argon is the M shell, and it has 8 electrons. These 8 electrons, otherwise known as the octet configuration in the outermost shell, gives noble gases their special stability, making them virtually unreactive towards other elements of the periodic table, the reason for the name noble or inert gases. Because of this stability, other elements of the periodic table try their possible best during chemical combination to achieve this octet configuration, either by losing, gaining, or sharing electrons. For instance, the group 1 elements, otherwise known as the alkali metals, would prefer to lose 1 electron to return to the octet configuration during chemical reactions. The group 1 element, which includes lithium, sodium, potassium, rubidium, cesium, these group 1 elements here would prefer to lose 1 electron during chemical reactions in order to achieve the octet configuration. Let's take sodium of atomic number 11 as our example. Sodium has the electronic configuration 281. So it has just 1 electron in the outermost shell. In order to achieve the octet configuration, sodium would have to either gain 7 electrons to become 8 in the outermost shell, or it loses just 1 electron to become exactly like the electronic configuration of neon. So in this way, sodium losing an electron to form sodium ion makes it exactly like neon, thereby achieving the octet configuration of a noble gas. On the other hand, the halogens, which include fluorine, chlorine, bromine, iodine, and astatine, belonging to the group 7 of the periodic table. These elements have 7 electrons in their outermost shell. Take, for example, fluorine. Fluorine with atomic number 9 has the electronic configuration 2, 7. So it needs just 1 electron to complete the octet configuration of its outermost shell. To do this, fluorine is very close to achieving the octet configuration, so it will rather prefer to gain an electron to add to the 7 in its outermost shell in order to get 8. So fluorine would always gain an electron. Similar to all other halogens, they will prefer to just gain an electron to achieve the octet configuration and become like a noble gas, in this case, neon. So this summarizes the octet rule, which shows how elements strive to achieve the special stability like the noble gases. Based on what we've explained, let's take a look at some few examples from period 3. This includes the elements sodium, magnesium, and aluminium. Sodium has atomic number 11 with electronic configuration 281. Now, looking at period 3, for sodium to become the noble gas argon in period 3 here, it would require sodium to gain a whopping 7 electrons, which is quite difficult. It's an uphill task for sodium to gain 7 electrons. So sodium would rather prefer to lose its outermost electron and achieve the octet configuration of neon, which is quite easy. It's easier for sodium to go back and become like neon compared to going forward and becoming like argon. Therefore, because sodium loses just 1 electron in its outermost shell, then the valency of sodium is 1, to be precise, +1. Similarly, magnesium has atomic number of 12 with electronic configuration 282. It's more difficult for magnesium to go forward, gaining 6 electrons to become like argon, compared to losing 2 electrons to become like neon. So magnesium will prefer to lose 2 electrons, and therefore the valency of magnesium is +2. Atomic number of aluminium is 13 with electronic configuration 283. So it loses 3 outermost electrons, and therefore its valency is +3. For the examples in period 2, we'll take a look at nitrogen, oxygen, and fluorine. So nitrogen has atomic number 7, oxygen has atomic number 8, and fluorine atomic number 9. So the atomic configuration of nitrogen is 2,5. That of oxygen is 2,6, while that of fluorine is 2,7. So nitrogen needs just 3 electrons to become like a noble gas neon, which is atomic number 10. So it needs 3 electrons to get the octet configuration similar to that of neon. So nitrogen will always try to gain 3 electrons to become like neon. So because it gains 3 electrons, the valency of nitrogen is 3, specifically -3. Similarly, oxygen needs just 2 electrons to become like neon, that is to get the octet configuration of neon. So it will gain 2 electrons, and therefore the valency of oxygen is 2. Similarly, fluorine needs 1 electron, and so it gains just an electron, and therefore the valency of fluorine is 1. So this principle can generally be used to deduce the valencies of elements in the periodic table. So based on this, the group 1 elements, the alkali metals, have a valency of 1. Lithium, sodium, potassium, rubidium, and cesium always having a valency of 1 +1 to be precise. That of the group 2 have a valency of +2. The halogens have a valency of -1, while the groups 6 have a valency of -2. It should be noted that some of these elements, especially going down the group of the periodic table, deviate from this principle because of concepts like inert pair effect and variable valencies. With all these, we've been able to see the reason for the valencies of elements, and it all boils down to the octet rule. Basically, elements in the periodic table strive to achieve the electronic configuration of their corresponding noble gas. This brings us to the end of the first section of this video. I implore you to watch the second part of the video so as to consolidate your understanding and give you a holistic view of the concept of valency. If you found this beneficial, please do like, share, and subscribe. You can also leave your questions in the comment section, and I will do my best possible to answer them. Thank you.